What is the strongest team you can build in Pokémon Champions? I created an AI and taught it how to play Pokémon so we could answer this exact question. Pokémon Champions is the newest battle-focused game in the series, recently released on both Switch 2 and mobile. This August, for the very first time ever, the Pokémon World Championships will be played on this new title. In this brand new format on a brand new game, even top players haven't yet cracked the code on the perfect team of 6 Pokémon. Can my AI do better than them? Previously on my channel, I wrote an algorithm that can iterate through hundreds of teams with millions of battles to shape, fine-tune, and breed the strongest possible team. Using the Worlds 2024 format, I ran over 5 million battles and arrived at a top-performing Miraidon team, which turned out to be pretty good. Does that mean my algorithm was perfect? Well, not exactly. The core issue was that my simulation could only pick random moves. For each top-level move it made, there were thousands of nonsensical moves creating noise. I had to run millions of battles just to get even remotely realistic results. There were just too many different variables to control for. Ultimately, randomized move selection was the simplest, but least accurate option. If only I could have a model that would make intelligent moves, then I could exponentially reduce the number of battles I would need to get quality results. But training an AI to play Pokemon? And play it well? That would be nice, but man, that would be a lot of work to write, and could it even be possible? So I started building the AI. The first step was going to be gathering data from real human players. I went to Pokémon Showdown, the top browser-based online simulator, and downloaded over 50,000 Champions Regulation MA battle logs. Taking those, I next needed to convert these to a format my AI could understand and interpret. It would need to see the battle state and all of its available options every turn. From there, it could guess what move it should make, then compare it with what a human player actually did, and repeat this process over and over until it could more or less predict what a real human would do in any given game state. This is actually how AI like ChatGPT were trained, just with predicting what words come next in a sentence instead of VGC Pokemon battles. After about a week of testing, I was finally able to get the AI to accurately interpret both the simulated game state and be able to translate game states out of the logs. Now I can begin the training. And here's where I came up with a clever little trick. Each battle log contains both players' decisions, which play out in the turn simultaneously. But in reality, each log actually contains 2 distinct game states, one for each player. One where player A's moves and decisions resulted in their victory, and the other where player B's decisions resulted in their defeat. And each with hidden information from the other player's perspective. By training my AI on each perspective of a battle, I was able to double the number of battles in my dataset. And if you know anything about AI, the more data you have available for training, the more powerful it can become. Now, with over 100,000 human battles, I kicked off the training. In just a few minutes, I had my first non-random Pokemon decision-making model. I threw together a simple team of the top used Pokemon, items, moves, and booted up the simulator. Thanks to Pikalytics, we can pull usage stats from the most common Pokemon, moves, items, stat spreads, and randomly generate what I would refer to as meta teams based on those probabilities. And the results were not good. The first battle was over 50 turns, and when it wasn't getting stuck trying to make impossible moves, it had all 4 Pokemon spam the move Protect until the PP was reduced to 0. As it turns out, Protect is the most common move used on nearly every Pokemon in VGC doubles, and when used in succession, it has a 70% chance to fail. The AI astutely learned that this move is at the cornerstone of VGC and was often the key to top players' victories. But what it didn't learn was that this really was only the case if it didn't use Protect on the previous turn. In human battles, Protect equals win, but in my AI battles, Protect equals a loss. I analyzed the human battles and saw that they double protected only about 7% of the time, a far cry from the nearly 100% my AI was performing in these first few trial runs. The problem? It only trained based on the options it had at every given turn, not making those decisions based on the results of the previous turns. Even though it would increase the complexity of the training by adding thousands of more variables, It was a necessary step to get these AI to see the whole battle. I added in those extra factors and trained it again, and the next results were promising. It was still double protecting 4 times as often as humans were, but I was able to prove that it was able to learn and adapt. So I fine-tuned the battle state further, adding a bit more complexity, handling some edge cases such as when Encore was used, taunt, choice item locks, etc. By the 10th iteration, my model was reaching human levels of move frequency and decision making. But humans can make mistakes, they can make risky reads, and can even win when making suboptimal moves. The AI was nowhere near perfect, and it showed. I had my latest model fight the original random decision model, the non-AI model, if you want to call it that, and it lost. Hard. It could only win about 1/3 of the games that it was playing, and the opponent was literally just throwing darts with a blindfold on and managing to win. Something still needs to change. By this point, my model was given only a single goal: win. It didn't matter if it had to make positional sacrifices or inopportune switches if that meant getting to victory. After all, the only HP point that matters in a game of Pokemon is the last one. You don't get extra points for winning a 4-0 sweep. I trained it this way so that it would not bias the model towards selecting only the most aggressive options. Strong players most often couple powerhouse Pokemon with support options to edge out decisive victories. The fix? A completely new approach to training the model. I wrote an entirely new training algorithm based on reinforcement learning with a method known as Proximal Policy Optimization, or PPO for short. Now, we would have the AI battle itself over and over again, and at each step of the battle, it would update its strategy in small, controlled steps. This way, it would not bias itself towards only aggressive plays, but learn from the subtle changes of the battle state. I introduced a new variable here, an HP delta, which would reward the AI at each turn for dishing out damage and taking KOs. This would start incentivizing the AI to nudge it towards victory, while still weighting a win much higher than a loss. And thanks to the previous training, we had a decent model based solely on human decisions that can be used as the starting step. Unlike the previous training, this can be ran iteratively. We can take the previous model and train it until we find a more powerful model, and then use that as a new base and repeat the process, having a new model battle the previously strongest model until it can surpass it, with that pesky random model thrown in. The results were immediately promising. The first PPO model defeated the human action model 60% of the time, and now was able to defeat the random model just over 40% of the time. An improvement, but it still irked me that we could not beat that dang Mankey on a typewriter. But this was only the first model, so we ran it again, and again, and again. And by the 7th iteration, it had finally surpassed the 50% threshold against the random model. By this point, we had hit a plateau in terms of performance, so I added one more piece of the puzzle, an entropy bonus. A bonus reward for not collapsing into a single strategy and continuing to explore new and creative options even as the model got more refined. PPO Model 8 was finally able to make meaningful improvement thanks to that entropy bonus, and continued to improve until we reached a new plateau by iteration 13. Far surpassing expectations, this new model was able to defeat the random model over 70% of the time. A 14th and 15th iteration were tested, but were not able to outperform Model 13. So there I had it. I finally had the brain to power a Pokémon Champions playing AI. And remember, all of this was done so that we could have a reliable brain chip to put into my best team experiment, to drastically cut down on the exploration space. Remember, there are more ways to build a single team of Pokemon to customize the stats, items, moves, etc. more than there are atoms in the known universe. And short of testing out each and every option, my metaheuristic algorithm aims to rapidly weed out underperforming teams and quickly pinpoint a winning team. We won't be sure it's perfect, but hey, we can't wait till the heat death of the universe to find out. A quick rundown on the experiment. Not much is changing from the last video. We are employing a genetic algorithm with simulated annealing. In short, we take a large, random population of diverse, meta teams, have them battle, and then sort them by their number of wins they were able to achieve. Then take the top performers and create a brand new pool of potential teams by breeding characteristics from them. We then repeat this process over multiple generations, and the algorithm anneals, or solidifies, reducing the mutation rate each time until the final teams lock in on winning combinations. A key note here is that we should never have the breeding teams battle one another. subtle biases can influence which teams perform well over others. For example, consider a team with only dragon Pokemon. Dragon is super effective against other dragons, so this team would perform well against other only dragon teams. So what would end up winning here across multiple generations is more teams that can defeat themselves, but that doesn't necessarily mean much versus an average meta player. And yes, this is the exact reason why nature avoids this in real life. In a traditional genetic algorithm experiment, you would keep the same population size and trial length each generation. But now that I had an intelligent AI model, I could cut out all that extra noise and instead use the same computation power on more battles to favor consistency. Real-life Pokemon tournaments start at the local level with relatively few rounds, where every Little Timmy and Youngster Joey face off against the occasional pro, where these locals weed out until they find the top players. Those players then qualify for larger regional and then international level tournaments where stronger and stronger players fight increasingly longer rounds to eventually crown the best players. And at the World Championship, you face a 3-day endurance round with over 16 rounds of Swiss before cutting to the top 16 players. I can have my experiment mimic this almost exactly, but at an even larger scale. And because we're solidifying the experiment every generation, in a way I'm now annealing the annealing. If we want to truly find the best team, we need to blow reality out of the water. Before we do anything too hasty though, I ran a small experiment as a proof of concept. With 100 initial teams, 20 generations, and starting with 3 best-of-3 matches before cutting down linearly to 16 teams by the final generation, who would eventually play 16 best-of-3 matches. This ran thousands of battles, and the final teams were interesting to say the least. The best performing team was one starring Mega Gardevoir, Mega Tyranitar, Mega Aerodactyl, Garchomp, Rotom Wash, and a Fissure Snorlax. Fissure is known to be the most inconsistent move in the game, always KOing an opposing Pokemon 30% of the time. The team won all 16 of its matches in the final generation, and I'm showing its Pokepaste on screen now. This shouldn't be too much of a shock, seeing as Fissure Snorlax teams have performed well and had top 8 placements in smaller tournaments, but let's turn things up a notch. The true experiment is going to have 1,000 random meta teams, enter a 3-round gauntlet, and only those winning all 3 of those matches will move on to the actual first round of the experiment. This rapid culling will really help save time by not computing battles for weak teams, only keeping the strong ones. Just over 200 teams cleared the first hurdle, and then began a 20-generation experiment. Each generation would scale from 16 best-of-3 matches all the way up to a grueling 50-round best-of-3 mega tournament by the 20th generation. The top-performing teams after each generation would breed with one another and mutate their moves, items, stat spreads, aggressively at first, cooling down each generation until only fine-tuned adjustments are made by the final generation. This was a bit of a doozy, with my computer able to compute about 1 battle per second and over 120,000 battles to compute. This took over 24 hours of non-stop computation to complete. I woke up to find that my house had not burnt down, and I had the results that could possibly contain the best possible team in Pokémon Champions, thanks to my AI model. So, without further ado, here's what we found. The best performing team with 49 wins and only a single loss in that final generation is Mega Tyranitar, Mega Aerodactyl, Mega Gardevoir, Sneasler, Archaludon, and Sylveon. This is an offensive team both physically and specially, favoring rock and fairy coverage. Is this going to be what takes the crown this year at the World Championship? Maybe not, but only time will tell. My algorithm can hone in on winning strategies to defeat the current metagame, but those meta trends are constantly shifting. A strong Steel-type Pokemon like Kingambit can threaten 4 of the 6 Pokemon on this team for super effective damage. The ever-shifting tides of the meta will always keep the idea of a single best team in a state of flux. And here I'll be showing a few of the other teams on screen now that also reached the top performance in that final generation. This project was a lot of fun to code and build. Combining the newest Pokémon Champions game with my expertise in operations research allows me to uncover insights into the game while pretending like my master's degree isn't completely going to waste. But in all seriousness, this was a blast. And the exploration of the Regulation MA Pokémon Champions format is only the beginning. I've been slowly capturing data for Regulation MB, and I'm excited to see how trends develop and meta shift while running bigger and better experiments. If you would like to stay up to date on new developments and future content, I will kindly ask you to subscribe and like the video. It helps out immensely, and I would really appreciate it. I have even more cool ideas coming down the pipeline, some related to Pokemon, some related to new developments, and it's all very exciting. So stay tuned. I appreciate you watching until the end of the video. This is Block Chicken, signing out.